Thank you. Oh, sorry. Hey guys, by the way, thanks for our wonderful recruiting teams that gave away socks. We love nothing more than people taking a picture wearing our socks and not mentioning Salesforce IQ, so please do so. Okay, so this is what I'm gonna talk about today. I'll introduce myself, and we'll talk about something that is, I think, doesn't get enough love in the kind of the machine learning space. By the way, thanks for everyone who's here and kind of missed some great streaming talks, because you will not get another chance to watch another streaming talk at this conference. And so I will talk about feature engineering, how people think about it, and what it actually is. And kind of more as a buffer of time, if we will have, I've a lot of things to go through, so I will also touch on some advanced topics and eventually just kind of present a summary of what we talked about. So a little bit about me, less fancy than kind of the intro I just received, but kind of a more formal one. I'm a data scientist, serial data scientist. I've been doing it long before it was actually called data science. Then I moved to the Valley, and I guess now I'm a data scientist. And I kind of tweet at Big Data SC, and just kind of something I have to say, even though kind of I have a slightly fancy title today. The stuff I'm going to talk about is actually code that I still the second top contributor to, so believe me, I know what I'm talking about, at least for that code. So let's start with a little bit context of what this talk is about. So when I joined Salesforce, and I'm part of what's called Salesforce IQ, and Salesforce IQ is the kind of a division of Salesforce that is in charge of creating machine learning platforms for Salesforce internally and its customers. And I do data science and engineering there, and kind of the first thing I came to Salesforce and they kind of told me about is, hey, we want you to build model for every one of our hundreds of thousands of customers, and because two issues. One is the privacy issues. You cannot really cross-pollinate those data sets. And second, because of also performance issues, what we kind of found out later, it's actually the usage of the Salesforce platform kind of varies so much. And just to give an example from my previous life at LinkedIn, I was working on the job recommendation algorithm. And for the job recommendation algorithm, so people who work at Google or people who work, bank tellers at Wells Fargo actually use the platform pretty much the same way. So you can build one job recommendation algorithm because you have the same features, you have kind of the same predictors, and you just go and build a single job recommendation algorithm. This is not quite true at Salesforce because the platform is so customizable that every single customer uses it very, very differently because it's adjusted to their sales processes in the case of our sales solution. And we have service solution and we have marketing solution. We have a bunch of those solutions. And the point is that customers use them very, very differently. So what we found out is that it doesn't really make sense to have one global model, one size fits all, and we actually need to generate all these models. But then even if I kind of, we hire every single data scientist in the Valley, we'll still not have enough to do that work and create a customized model. So we had to build a framework that basically we kind of refer to it as metadata science. We had to teach a machine how to do data science and how to automate most of the day-to-day tasks that data scientists actually do. And this is what the talk is about today. So again, one kind of takeaway that hopefully you will take is feature engineering is not an atomic operation. It's not the one thing that a lot of people say, hey, I will just do feature engineering. It will actually, I'll go over a list of 10 different things that fall under that bucket, and I will touch on every single one of them. Most of the steps can be automated, and this is kind of the second takeaway. So for the first is like, let's say, if you're an engineer, kind of never really practiced a lot of machine learning, you will hopefully understand a little bit more about this, craft that is called kind of machine learning. But if you are a very seasoned data scientist, hopefully what you will take away from this presentation is how to automate a lot of the steps that we keep repeating again and again and again. And the first thing that will also, something we just found out, is after we took Scala and Spark, because, well, they're awesome, but it's also we learned a lot of along the way that what we actually did would be extremely more difficult if we would have chosen a kind of a untyped, dynamically typed language like Python or something else, and actually the kind of strong type and a lot of the functional characteristic. And Malcolm Greaves covered a lot of it very well in the talk before I did. Is it's actually great for machine learning pipelines. So let's begin. What is automated machine learning? And here I'll take an actual example for a very kind of common data set. I hope you can see it, but it's the Titanic data set. It's basically a list of people that were on the Titanic with some features on them. And eventually the important part here, as you can see, is kind of one of the things that people like to predict about, who actually survived the Titanic and whether we can kind of build a model. And the reason why I take the Titanic example, and I will talk about for 40 minutes about the feature engineering that goes into that data set, the point I'm trying to make, this is probably the most trivial data set that you will ever encounter. You will never encounter such a trivial data set in real life. And then still, I will give now like a 40-minute presentation on how actually you do data science on that trivial data set. And just to give kind of the other extreme of the spectrum, so when I was working on the job recommendation at LinkedIn, we were 2 people, and only to understand seniority, like for example, to learn from the LinkedIn data set that a VP is kind of higher than director, is higher than a manager in the tech industry, it was a feature engineering work of 2 people for about a year. So, and basically what I'm will try to show here that is a lot of the step can be automated here, and I will show kind of how it's done. And it will be a very, very partial talk, but again, we only have the time that we have, so hopefully we'll learn from it. So the platform we created is called Optimus Prime internally, and we call it Optimus Prime because it's just a bunch of transformers. Get it? Thank you. And basically, those are the kind of 10 steps, and I kind of took it from a tutorial that someone written very eloquently. It was first written in R, and then someone adapted it to scikit-learn about basically taking the same data set and doing a tutorial of those 2 tools and around how to kind of classify the survivors with that data set. And I will go through the same thing, how it works in Optimus Prime. And I will talk why actually we need Optimus Prime differently. The one thing I will kind of not talk about is actually kind of the runtime environment and how it works internally, because there is a talk given by Liam McGuire from my team that she kind of went in QCon very deeply into it. There is no point to rehash it. If you don't remember that link, well, first I will post the slide. The second is just you can look Salesforce Machine Learning QCon, Salesforce Machine Learning InfoQ, and you will just find it will be the top results in Google. So you can watch this talk because it will give the other aspect of kind of more the runtime environment. I will talk more about the design decisions that led us. And so one thing to understand about Optimus Prime, it's a tool that makes data scientists far more effective. And the way we decided to do it is by, instead of data scientists to start writing code from scratch, we basically build them a code gen tool that takes a data set and basically generates a lot of code for them to start as a very, very good starting point for the data exploration, when they can go and then do more and more feature engineering and all the things that kind of data science go to. And by the way, for most use cases, we actually not even do that extra feature engineering and we just deploy it. But kind of the point of how it works, this is OP stands for Optimus Prime, and we took the SBT whatever gen idea, we give it Titanic CSV, and then dash label. There are a bunch of other features, but basically that is how you kind of generate that code. Generate code. I will go into slide because unfortunately, like I tried in a previous while working on the stock saying, hey, I'll show you the code in live, but it was a massive amount, and I think it was missing the point of, there was a lot of stuff in there that the data scientists who work with this kind of day-to-day understand, and I think it wasn't as good for the point I was trying to make, so I just took some of the parts and put them into slides, but basically that is how it's done, and the rest is magic. Okay, thank you. No, I'm kidding. Okay, let's go into it. So the first step is feature classification. And what do I mean by feature classification? If you look at this data set again, you will see that the features are actually of different types. We have some numeric, we have some categorical, we have something in between. And this is the first thing that, and obviously the treatment that we would like to, as a kind of a data scientist, to do for every single feature, we'd like to treat them differently. And a lot of time is actually going explicitly saying that this feature is that and this feature is that. And this is kind of a part of this is how the generated code looks like, and you can read it, and again, I took it just to fit into it, but you can see that it generated, so now we have kind of a real val that we can actually, now is something of type feature, in this case is categorical, and again, this is not code that was written, this is a code that was generated. That's important point, and that is the point of would be at all. And here you can see that the passenger class was, the age was numeric, the class was categorical, and survive is actually a binary feature that was generated. And you see there is also part of the builder pattern is as response, because we deal with the feature that is actually the predictor, the response we deal internally differently. So this is kind of now into that feature. There's a kind of bunch of steps. It's a trait that behaves in a different way. But this is kind of not not amazing yet, but it's still kind of, what's great about it is now you can actually address all those features instead of parsing strings, separating by comma, doing all this crappy stuff like no one likes to do, is now you actually have strongly typed features that you can do a lot of pretty cool stuff with, and I'll show some of them. The other thing is actually we have derived features, which is the features that we kind of don't really see here immediately. By the way, something I forgot to mention, the reason why we have here this Titanic is kind of a legacy, unfortunately, we still kind of haven't fixed it, is because we first implemented for Avro or case classes, and then we kind of, in order to make it work for CSV, we first convert the CSV to kind of case classes and then apply it, but basically that's the same. So derived features, here you can see there is this home destination column. And the home destination is not just a string, right? It's actually, there is a little bit more logic to it. And this is something that Optimus Prime actually captures as well. So first of all, this is the same feature that you could see as well. It's just categorical. But in some cases, and this is kind of a statistical method that it goes through, in this case, is a bunch of regexes with some priority, and it tries to classify every feature. And if it sees that over a certain percentage of the features matches to some pattern that we recognize, then it actually goes and creates those features as well. Again, not something that is mind-blowing by itself, but it's very, very useful because people don't need to do it themselves. And here you can see that Optimus Prime identified that we have a city, and it extracted it with a reg extractor, and it recognized that there is a state, and it extracted it with the state. And the regex looks something like, if there is, string, comma, and then one of the 50 acronyms for a state or their full names, then it kind of captures those two variables. Again, not mind-blowing, something that requires a PhD in machine learning to come up with, but it's actually very, very useful because on kind of larger data sets, you have more and more of those types, and because now this is actually, even though it's categorical, it actually builds a feature of type city, feature of type state, is we will kind of use that information because those features actually have additional functionality that just a categorical feature does not have, which is kind of cool. Missing values. This is something that, again, data scientists deal with every day. And the problem with missing values, there are multiple of them. One of the problems with missing values is that like algorithms, just if you take a just Spark ML logistic regression, it just does it expects to get a dense vector. It just doesn't have like a vector of options. Like you need to get it like a vector of numbers because that's how it works, or data frames, or whatever. Some algorithms just don't deal well with missing values. So there is the practical problem. The second problem is actually when you have many missing values, like you can see on this, it might be that in that case you will get better performance if you actually fill in the missing values. It's just a performance. So one of them is just practical consideration. The second is a performance consideration. You will get a more accurate model if you actually do something and not just have missing values. Because again, decision trees or random forests, there are some machine learning algorithms that deal with missing values. But even them, if you do some stuff around missing values, they kind of do it more accurately. And this is some of the code that is generated for it. So you can see that we have the age value that was actually defined before, and this is now like a different class that I'm showing. And what it does is just we created a, it has a method that's called .fieldMean, which creates a new value, which is field age. So the second line here is just a syntactic sugar. You can achieve the same, which is basically what it does, is age.transform, and then we have a transformer, back to the Optimus Prime thing, is, like it has a pretty long name, mean numerical imputation transformers. We have statisticians on staff that are very proud of their craft, and they like very verbose naming. We need to work on it, but the point here is that you can see that, for example, in the age, and this is, by the way, configuration. So this whole thing, this whole code generating has a pretty big configuration file. And for example, one of the things you say in the configuration is that the appropriate way to fill in missing values for numeric fields is use the mean transformer. The proper way to fill the categorical field, which is that home destination, is to use the mode transformer. For those of you who are not statistician, mode is the most common term in a data set. So now we have, and again, basically there are more of those long, and kind of in order to keep the code a little bit shorter, we actually generate those lines only for the features that actually have missing values. So if a feature doesn't have missing values, we'll not just call this function to do nothing. Okay, next. So now we come to the kind of transformation, and this is where probably most of the kind of work happens, and coming with way different ways to do kind of more and more transformations. So for example, some of the transformations that you can do are taking the age column and normalizing it. That is one thing. So why would you want to normalize a variable? So for example, for algorithms like logistic regression, that are basically kind of this weighted average across multiple features, in order to make sense of the weights after you apply the algorithm, you want you want all your kind of feature, or all of your values to be normalized. Let me repeat it again because I don't think clear enough. So, like for example, if we use two features and both are weights, but one is in kilograms and the other one is pound, so the weight before the pound, because pounds are just higher, just bigger numbers that represent exactly the same thing. So the weight there would be bigger than the weight before the kilograms, because it's just linear operation. You multiply one number by the other. So in terms of being both of them equal, you will need to multiply the kilograms by by a bigger number than the pounds. However, because people like to understand the meaning of those numbers, a lot of people, when they look at a linear regression equation, they want to see which variable, which feature has the higher weight, because it also kind of means that, oh, this feature is kind of again, there's some hand waving. Please don't, like statistician in the audience, don't kill me. But it kind of implies that this variable is more important. So in order to actually get this added benefit of understanding which feature in your data set is more important than not, you need to have all your numeric variables in your data set actually be normalized to the same thing. I try to explain it in two ways. If it's still not clear, please blame me for not explaining it right. It's, yeah, I need to be better at it. But going to it is we actually have several normalization techniques. So one of them is just normalize. The other one we use is actually bucketize, which is also very common. We use it both for categorical variables, and we also use bucketization for kind of numeric variables. In this case, is fair. So the question is, why would you want to bucketize a numeric field? So, and the thing is, again, the example here gives, like, for example, if you take your weight as a function and then you try to predict, how far you can throw a javelin, then you will see that it's actually not a linear function, because obviously, grown men probably throw javelin farther away than kids. So in that case, it's kind of linear. But at some point where, let's say you become morbidly obese, it doesn't mean that you kind of throw javelin farther away than a person that weighs 4 times less than you. So I'm saying in most cases in life, actually the linear relationship between kind of data sets are kind of does not hold forever, and this you probably would want to make kind of bucketize even kind of the weight, which is a continuous variable. Want to bucketize it for the weights of children, and then kind of the weights of adults, and then the weights of adults that are maybe kind of over the weight where it becomes kind of optimal, because there is probably some optimal mass of javelin throwers or something like that. And so what bucketize does is basically takes a variable, whether it's categorical or continuous, and basically breaks it into n kind of n binary variables. So basically, once we decided a bucket, then that feature will now represent whether the kind of that record is within that bucket. So for example, if in my example, the weight is between 0 to 100, then there will be a binary saying, hey, whether that person's weight is between 0 and 100, and so on and so forth. And the thing to see here is, again, yet another configuration thing that actually we found out that the way to bucketize continuous variable, because like the mean elements and max depth, like we shouldn't go too much into it because we can spend an hour only talking about like proper bucketization techniques. But the point here is that it's kind of based our implementation on decision trees, and that's kind of parameter that what we found that kind of works around finding kind of good bucketization for the features that we use. And again, that is all generated, and people can just go and change that number or change the configuration if they find that they need so. Okay, augmented features, this is actually, I would say that is, we still haven't implemented that, but it's just, I saw this cool demo about a company called Spark Beyond, and I said, oh my God, that's like so cool. We need to have it as part of our, but this is kind of, so this is the part that is, does not really exist, but I want to say that this is definitely a part of what a lot of data scientists do, that once we identify that we have our home destination is city and state, we can go and pull a bunch of stuff, like for example, and this is again something data scientists do very often. They take and you can look at the weather. So maybe the weather from the city that this person from had some play in around how well they deal with cold, like the cold water where the Titanic sank, and maybe that's a predictor. I'm saying the median income might be, again, another variable. You can take their zip code and transform it to the city, go to Wikipedia, find the median income or some other data source for that city, and you can kind of create a bunch of these features once you have better annotations around your variables, and like much richer types, which is kind of what we have, than just string or categorical. You can actually do all of that transformation about going to different data sources and just pulling almost kind of everything that you can think about from those data sets. And this is kind of a fairly common technique that data scientists do, but it's actually an extremely tedious manual process, and this is something I would love for us also to do in the platform automatically. The other part that actually does happen and quite often is there are interaction features. So what are interaction features is sometimes a feature does not kind of make sense on its own, but if you combine two features together, they start making kind of more sense. And one of my favorite examples was from a PhD dissertation of a LinkedIn colleague of mine. She did some bird migration patterns, and she had this like beautiful visualization to show that if you look at kind of bird coordinates over the course of a year, it just looks randomly, it just spread all over the map. And if you look at weather, it's also, spread all over the map. Like, every weather exists at some point of the year at every place. When you take those two variables together, you actually see a distinct pattern where, birds are actually kind of in the warmer places kind of all the time. And by combining those two variables, you actually see a pattern that without those two variables, I tried to find an example, I couldn't find something that's very good. And hopefully we find out. But in this Titanic use case is actually, because again, we run it, the gender and age. So this is basically, we're taking a categorical variable, we kind of multiply it, and this is not the the algebra normal multiplication operations. Like I said, our features have those kind of added functionality. One of them is a multiplication, so we can actually multiply features together. So when we multiply age by fair, it's just a simple numeric multiplication. When we take a categorical variable and multiply it by a numerical variable, it actually creates another categorical variable, which is kind of the concatenation of those two variables. And kind of gender and age, we found that actually kind of works pretty well. It does add additional information that you don't get by using only gender or only age. The problem with that, and by the way, the augmented features examples I showed before, there is kind of this huge problem that if you create every single feature combination that you can think of, and this is, by the way, I think there was like 9 features here, so the combination, you can kind of do the math. I think it's a little bit more than 9, but it's like several hundreds of those features, and probably can be several hundreds or thousands more from the augmented if you pull anything you can think about a city, about a state, about an age, about whatever. You get to just a variable explosion. So besides the computationally hard nature of that problem, there is another problem that you will start seeing things that do not really exist. And this is one of my favorite examples, is there is the website that just finds correlation between random things. In here case, you can see that the divorce rate in Maine correlates with per capita consumption of margarine in the US, and the correlation is 0.99, which is like 1 is the maximum. So basically it means it's perfect correlation. And believe me, if you throw, and the whole point what this website does is just takes as many data sets as possible, and then basically you have the cross product between all those data sets, and you'll find one that is has a correlation of kind of 99, and this is something that you have to be extremely smart into avoiding. And I'll talk about how we deal with it, but before this is another very common problem that we have to deal with as well, and this is what's called label leakage. As you can see, even in this data set, we actually have 2 additional columns. And the column, one of them is boat, which probably, if you were in a boat, you probably survived. But even more, there is a body, which represents some identification of your body. So, if you have a body number, you probably did not survive. And that's a perfect example of label leakage. But if you think that this is a contrived example, believe me, it's not. Here's another example where, after you buy something, you get a thank you email for buying something, and there is a lot of people that say, hey, let's look at your email activity for e-commerce things, and then you see, oh yeah, you create this thing, everyone who got this email that has this word thank you in it suddenly, is very likely to buy. But this is a perfect example of label leakage, basically relying on data that will not be there in time of scoring. And there are other many ways. It's actually an important problem for inside Salesforce. one problem that we have that, for example, when when clients close records saying, hey, we closed that deal, then they go and add a bunch of information about that deal. And then I say, well, if the deal has zip code, it's very likely to close. But no, it actually happens after. And because it's like, this crude database, I actually don't have the timestamps. And now I feel, I create, there's another like perfect label leakage. There are more and more examples. So we kind of deal with that automatically. So this is kind of the code that actually eventually generates the model. And you can see here there is something that's called sanity check true. And what the sanity checker does is deals with this multicollinearity, wow, that's a mouthful, issue, which is basically trying to find perfect correlation between any two variables and removing them from the data set. Another cool thing that I will touch very shortly is please take notice of why the positive response ratio is an array, because I'll get to it in a sec. So this is kind of goes part of the resampling, and this is one of the problems. If you think about, like, for example, fraud detection problem, in fraud detection, like the likelihood of actually a transaction to be fraudulent is extremely low. So let's say, it's like, 0.01% of your actual transactions. The problem with that is if you have a model that says all your transactions are actually non-fraudulent, this model will be 99.99% accurate, which is great for any real problem. But it's actually, obviously, it's a completely useless model, right? And this is one problem that we have to deal, because around our hundreds of thousands of customers, we sometimes deal with customers that whatever the event we're trying to predict, like 0.1% of likely, and sometimes it's 10% likely. And we actually need to build our training set accordingly. And the way we do it, we actually try to go through several of those, and we actually compare. So in this case, it's pretty kind of dumb. It's like research. We just try all combinations, see what works best. But I will go even further, because you will see we don't only look at that parameter. We go to a model selection, this is a kind of scikit-learn. They kind of classify them all, but you can see there are multiple models that can work. And what we found across our many customers is actually sometimes a linear model works better, sometimes a forest model works better, sometimes some other model, and we actually don't really know. And the thing is, we actually say, hey, we don't have to know. What we can do, and this is kind of a wrapper of Spark ML pipelines, is why not try multiple things? Why not try logistic regression with these regularization param and these elastic net params? And why not try random forest with a bunch of these params? And basically, it's a cross product of all of these params. And then once we actually try it, this is when we have this function called try models. We give a training set, test set, models, and this is where we set the metric. And the metric, A, U, or C, doesn't really matter what it is. It kind of goes and create all those models. We're actually smarter than just going brute force through those, and there is a bunch of packages that kind of do it for you, including I think Spearmint and BigML and some others that kind of do a smarter search around that space that kind of converges much faster than just trying all options. So I definitely would recommend to do it. What's my timing? Just 5 minutes. Awesome. So I'll skip the advanced topics because I really would much prefer for you guys to ask me any questions you have. So just kind of to wrap things up, this is what kind of I want to say. So machine learning is kind of very complex, and very complex. I'm not saying like no one can do it. I'm saying just it's not the one thing. There's like a lot of things that some of them are kind of domain expertise, some of them just stats knowledge, some of them just like experience of knowing what a label leakage is and what the various form it can manifest in, and to be prepared for it. Most of the steps can be automated. Like I said, all the code that you've seen is code that automatically generated. It actually achieves very good results, even without touching it. So we have a benchmark where we have like, I don't remember, a couple of dozens of data sets. And the way we iterate over our platform is, we have this kind of regression test that every time we improve the platform, we go and kind of run it across all of these and see whether improve. And again, while I didn't touch it and it explicitly, believe me, everything I showed is possible because Spark lets us deal with scale and with parallelization, and Scala gives us this wonderful type-safe static system, and really that made our life easier. So here is my shtick. If you're interested, if you're curious to know more about how Heroku, Prediction.io, the top Scala project on GitHub, and MetaMind fit together, please come talk to me, to any of our recruiters, any guys you see in the audience wearing the IQ t-shirt. We are hiring, and thank you very much. So the person who asked the first question gets another pair of socks. Here. Oh, sorry. Oh. Sorry about that.
So I want to ask you.
Sorry, there are new socks. We haven't used them.
About the training. Do you do the training as well here, or do you do the training outside of this platform?
Sorry, you're asking whether we do the training?
The training of the model, yeah. Like doing the exploitation of the model.
No, so definitely what I showed here is, where's the clicker? It will probably take forever. But as you see, val best model, that val actually holds the best model eventually. So it's when you run it, that is the best model, and then you can decide. Like I don't show the code here, but you can either write it and score with it, do a bunch of stuff. But it actually holds what after we train all the combination of the models, that will have the best model in it. Yeah, so basically that thing goes into production. The one thing and this is you can see at Leah's talk, and I haven't touched on it, is actually you need to remember that in self-first context, that thing will then get applied and will generate a different model per customer. So it means we'll have, in the linear sense, we'll have a different weights for every single customer. So that thing will be then applied many times in parallel fashion. Yes, there.
Very nice presentation. First of all, it's a different thought process altogether. My question here is, can I safely assume the overall model is the factory design pattern plus the old reusable modular program to generate a code to do most of the things in automated fashion than building something scratch?
So sorry, just to make sure. So you're saying, could you assume that all that code is a the reusable fashion to generate all those models?
Right. Plus, they're using the factory design pattern models to compartmentalize those.
Yeah. So this is basically the thought behind it, and while not to be too philosophical, is bringing the same engineering practices that exist for decades on engineering to data science. So for example, all the features that are generated are actually part of this object that you can then extend and create more and more. Because at Selfers, one of the good things we have, at least, we know the data space that we're dealing with, and then we can already create a bunch of very sophisticated features based on this, and then you, as a data scientist, you can extend that, get all that wonderful functionality, and then apply. Again, it's really the object-oriented model where you just extend the class and you get all that functionality. Plus, you can remove from it, and you can add your own features. Yes, there is a question here.
Yes. So in this, we are looking at a very small data set, pretty straightforward and simple data set. But when you want to do in production and at scale, what are some of the things what you have experienced or seen to make sure the scalability is managed for these machine learning models?
So the reason why I run data science and engineering is, unfortunately, here's the data science part. My larger team is actually engineering to make sure that this thing runs at scale. So first of all, the thing I don't show here, all these transformers are actually, and again, I'm going to go geeky here, they were actually all implemented as monoids, and in order to ensure parallelism across, and we do it in Spark. So today it's still legacy, we use RDD. I can't wait for Spark 2.0 to try the new data sets. But the point is, it's everything that is generated is a Spark code, and then on top of it, we also have a very smart, because we run thousands of those models in production, and they run on Amazon on different clusters. So there is also a lot of sophistication that the engineering team built. And again, if anyone interested, please come talk to us. Is around how to take the data and the size of data, because they vary tremendously. We have customers that are 3 orders of magnitude larger than other customers. Is to take that data and realize what is the size of the cluster, how we tune the Spark jobs, and a lot of that goes into, and that also all fully automated. Yes, please. So I'll repeat the question. The question was whether there was a feature reduction space. So definitely. So this is, if you remember, there was the sanity checker equals true. So the problem with the feature reduction is, again, getting in the right mindset, the feature that will be relevant for every single customer will be different. So that is something that in the runtime environment happens, is that is the template, and then the sanity checker equals true is basically reduces a bunch of features, some of them just based on pure correlation with a label that is too good to be true, and there is like label leakage, or multi-collinearity if we have 2 features that basically are extremely correlated with each other, and some of them are just because we want to have the jobs run in a more performant manner, so we just reduce to the in the model that starts probably has like thousands of features. The model that eventually gets is probably dozens of features, so there is like a very large reduction space. Okay, I'm sorry. So apparently I'm out of time, but please come see me outside. I'll be happy to answer any more questions you have.
Thank you, Vitaly.